Hello, this is Dr. Farouk Aleimi, and I want to talk to you about control charts. This is one of the first in a series of discussions and lectures on control charts. The purpose of this particular lecture is to provide an overview of control charts and its applications in healthcare. We make a number of assumptions. We assume that you are familiar with basic process variation issues, that you understand simple statistics like measurement of central tendency, and we assume that you're interested to find out what type of chart is appropriate and to understand how to interpret control charts. You may wish to refer to other sections in this series of lectures where we actually show you specific charts or where we show you how to construct charts on Excel. A control chart is a graphical display of data over time that can differentiate common cause variation, that is, the variation that is inherent in every process and is due to chance, from special cause variation, that is, variation in a process that's due to some unassignable cause outside the process. In short, a control chart is a graphical tool that can help you decide whether the variation has led to fundamental changes in the process or is simply random chance observations. In the late 1920s, Walter Shorts, a statistician in AT&T Bell Laboratories, developed the control charts and its associated rules of interpretation. Since then, many others have added different kinds of charts. These rules identify special cause variations and are based on the probability that a graphical pattern would be very unlikely to occur by chance alone. Control charts consist of a run chart displaying the measured data over time. We turn to this next. A control chart is drawn so that on the x-axis the time is shown, on the y-axis a measured characteristic is shown. Observations are typically drawn as single markers. Here we see them drawn as triangle markers. The upper and lower control limit are usually shown by a straight line. The upper and control line are drawn so that 99% of the data should fall within these two limits. Any point that falls outside then can be interpreted as a radical departure from the pattern. A control chart can be an effective way to look at a process over time and to identify the presence of a special cause variation. This useful tool can help identify the appropriate actions to take when wanting to improve a process. That is, if a special cause variation exists, it's important to remove it before beginning work to improve the process itself. In addition, a control chart can be useful when evaluating the effectiveness of change. The control charts values are calculated according to the type of data being graphed. The formulas are specific to the particular control chart chosen. Sometimes the lower control limit turns out to be a result that is not feasible and should be set to 0. For instance, it's not possible to have a negative quantity of defects, so the lower control limits should be set to 0 instead of the calculated value. Likewise, sometimes the upper control limit may calculate a value that's higher than is feasible. For example, when satisfaction ratings are more than 100%. When this occurs, the upper control limit should be set to the highest feasible number instead of the calculated value. In this graph that you see here, you see that 2 points have fallen outside the control limits. These points should have special causes that will explain why they have fallen outside. These variations are no longer due to chance. 2 points are also within the two limits, the upper and lower control limit. These 2 points continue the process as it has been, and therefore they are just random variation. A key issue to settle before starting with any control chart is how many data points are needed. A trade-off needs to be made. On the one hand, the more data that we collect, the more time is taken, the more delay, and the relevance of the decision is lost. The process continues at fault and risks harming patients or wasting funds. On the other hand, if we collect too few data and rush to judgment, we have less precision and the limits are typically wider. The fewer the data points, the wider the limits. And our ability to detect a special cause variation would be lost. A trade-off needs to be made between more delay and less precision. Generally, 25 data points are judged to be sufficient. But typically, in many healthcare decisions, we use smaller number of data points. We use smaller data points because we want to do approximation, or if we have too few data points, we may be able to increase the number of observations by looking at finer time periods. For example, instead of looking at quarterly values, we might look at monthly or even weekly values, increasing the number of observations. Keep in mind that observations should be always independent from each other. So if the data doesn't change from one week to another, it doesn't make sense to look at the data on a weekly basis. But if the data changes on a monthly basis, then we can look at it that way. And keep in mind that the basic idea of control charts is to help teams improve care processes. There is no point in gathering data to statistically establish something if it does not lead to improvements. It's important to realize that control limits can be set based on the entire data set, as we see on the left-hand side, or can be set based on a portion of the data set, as we see it on the right-hand side. Here we know as a matter of fact, we know that the first 10 days were pre-intervention period, and the next 10 days, days 11 through 20, were post-intervention period. Since we know that something has changed on the 10th day, we calculate the control limits once for the first 10 days and different limits for the subsequent 10 days. As you can see, the results are quite strikingly different. When we calculated the limits for both 10-day periods, the entire 20 days, some data points on the first few days, the 3rd through 6th, would fall outside the limit. But when we calculate this and split the data by the 10th day, we see that a real new insight is gained into what has happened to the process. That the real thing that has happened in this process is the limits have changed. The underlying properties of the process has changed. There are many different control charts. One of the most famous is XMR chart, or the Shorts chart. X-bar, 2K chart, timing between chart, and P chart are examples of other charts that we will discuss in this series of lectures. Risk-adjusted P chart and risk-adjusted X-bar chart are still modifications of some of the more popular methods of charting. There are many different things that we might chart. One way of looking at the data is to see if they are continuous variables or events, discrete events for which we can calculate rates. Examples of continuous variables are length of stay, average length of stay, average age of a specific patient population, process turnaround time, staff salaries, severity of medication errors, individual patients' weights, blood sugars, cholesterol levels, temperatures or blood pressure over time, patient satisfaction averages over, assuming that satisfaction is measured on an interval scale, infection waste poundage generated, electrical usage, wait times, accounts receivable balances, time in restraints, time before hanging up the phone, and SF-36 scores, which are health status scores. Examples of discrete events are number of employee accidents, number of patient falls, nosocomial infection rates, percent of patients in restraints, medication error rates, adverse event rates, C-section rates, number of dietary tray errors, number of delinquent medical records, percent of patients with insurance, percent of patients who rated the facility as excellent, telephone abandonment rates, pressure ulcer rates, employee injury rates, percent of records that contains appropriate documentation. These are all events for which we have calculated percents and rates. If you have to decide which chart is right, you have to first decide if the data that we are plotting is continuous variable or a discrete event. If it is a continuous variable, then you have to ask yourself how many observations we have per time period. If we have one observation per time period, next you have to ask yourself if outliers are likely. If outliers are likely, then 2K chart is appropriate. If outliers are not likely, then XMR chart is appropriate. If multiple data points are observed per time period, then X-bar chart is appropriate. Now let's turn to discrete events. If we have a discrete event that we are trying to understand, for example, mortality, if the event is quite rare, then time in between charts is appropriate. If the event is not rare, then the P-chart is appropriate. By rare, I mean that the probability of seeing the event should be at least more than 5%. And finally, in all of these charts, if case mix changes over time, then risk-adjusted control charts are more appropriate than unadjusted. One final point about risk adjustment. When case mix changes over time, always use risk-adjusted control charts. In separate lectures, we will discuss what we mean by risk, what we mean by case mix changes. But if you are familiar with this concept, and if you are aware that your case mix is changing over time, then always use risk-adjusted control charts. For example, if you're looking at C-section rates, and you're trying to reduce them, but your activities has led to different kinds of patients being attracted to your hospital, people who don't want to have C-section, then you haven't really improved the process. All you have changed is attracted a different kind of patients who don't need C-sections as often. Keep in mind that when you do risk adjustment, instead of comparing to historical patterns, you're now setting your limits and comparing your observations to expectations. Risk-adjusted control charts are basically calculated by applying the formulas for control limits to the difference of observed and expected values.